We now stand poised to prove the measure extension theorem. Now, a warning. This is every measure theory student's least favorite part of measure theory. And there's a reason for that. The standard proof, which you'll find in every probability and real analysis textbook, which was constructed 100 years ago, is very technical, very unmotivated, and very hard to understand and remember. We are not going to take that approach. We are going to follow a totally different method of proof, which is natural, well-motivated, and beautiful. And it was developed right here at UC San Diego by Professor Bruce Driver. Let's begin. The theorem we're trying to prove is the measure extension theorem. We start with any pre-measure space. Mu is a countably additive measure on the field A. We construct Caratteodory's outer measure from it, defined like this from last day. The theorem is that although that outer measure is typically not a measure, indeed it is defined on too large a set, the full sigma field of all subsets, to be a measure in most interesting cases, it does restrict to a genuine countably additive measure on some sigma field which contains the field A. And note that since M contains A and is a sigma field, therefore the sigma field generated by A is contained in M. And so typically one might state the theorem that minimally the outer measure restricts to a measure on the sigma field generated by A. Let's just note right here that the question of the maximal sigma field to which one can extend a premeasure is a very deep and technical question, which is beyond the scope of this course, but may be relevant for some further study in probability theory. Now, this theorem was proved first by Fréchet using ideas from Caratteodory. There was also some involvement and independent proofs by Hopf and Kolmogorov. You might find all of their names attached to it in various combinations in different textbooks. But all of the proofs in all of the textbooks follow the same standard outline. The putative sigma field M is defined like this. Now you can stare at that formula for a while and understand that it's the sort of condition that must hold for sets in a sigma field on which mu star is going to turn out to restrict to a finitely additive measure, and eventually countably additive. But in my experience, no number of times staring at that formula will give you any deeper understanding of where it came from or what it's really supposed to mean. Nevertheless, one can then show that this is indeed a sigma field, that it contains the original field A, and that mu star is a countably additive measure on it, concluding the proof. All of the proofs of these facts require at least one new tool that we have not added to our tool bag. Many of them use something called the monotone class theorem. Some more modern adaptations of the proof use the pi lambda theorem proved by Eugene Dinkin. We will circle back and develop a version of Dinkin's pi lambda theorem called the multiplicative systems theorem later in this course. But right now, we don't need it because we are not going to follow this approach. Now, I should add that the standard approach does have one advantage over the one we're going to follow. It works for all premeasures. The one we're going to follow only works at the beginning for finite premeasure spaces. Since this is a course in probability theory, that isn't a big restriction. Our most interesting measures will be the ones of total mass 1, which are finite measures at the end of the day. We will have occasion to consider some sigma finite measures that are not finite measures, but we'll see at the end that we can extend Driver's approach pretty easily to those. And so the large disadvantages of the standard approach its technical unmotivated difficulty and the fact that it is simply too clever by half to really understand really drives home that driver's approach is the way to go. So let's get into it. We start with a finite premeasure space. That means that mu is a function from our field into some compact interval, from 0 up to a number, which is mu of omega. Our goal is to extend that function mu from a to a function mu bar on some set containing a, which has nice properties, that is a sigma field, and so that this function has properties as nice as the original one. Driver's approach is as follows. We take our premeasure space sitting inside the subsets over omega, and we take that set of all subsets and turn it into a nice topological space. Then we define the extension of the field A to be the closure of the field A in that topology. We prove that the topology we've chosen is adapted nicely to the original premeasure so that that function mu is a very continuous function, continuous enough that it automatically extends to the closure of the set A. And then we will use basic topological tools to show that indeed that closure is a sigma field and the extension mu bar is a countably additive measure. Now it will turn out, and be useful in the proof, that the closure extension of the function mu is going to be equal to the Cartier-Dori outer measure generated by mu. So that's the philosophy that we're going to follow. When we want to make an extension of a function, we consider its domain to be a topological space, and we use topological considerations to extend it to the closure. So how do we turn 2 to the omega into a nice topological space with the topology somehow adapted to the premeasure mu? Well, ideally, we'd like it to be a metric space. Let's briefly review what that means. We call a space X a metric space if it comes equipped with a function d on x cross x, taking values in the non-negative reals, with these 3 properties. 1, the distance between 2 points is 0 if and only if those 2 points are actually equal. 2, this d distance function is symmetric. And 3, the distance function satisfies the triangle inequality. Now, when we have such a metric space, an X equipped with such a D, then we have all of the standard notions of point set topology, which are as nice as they could possibly be, and we can do standard analysis. We talk about sequences in the metric space X. A sequence has a limit, a point X in the metric space X, precisely if Weierstrass's definition holds that for any small tolerance, we can find some index n so that for all later indices, the distance between xn and the limit x is as small as the tolerance we chose. We can use sequences to define closures. Given any subset of our metric space, its closure is the set of limits of sequences that live in the set V. And in particular, the notion of a closed set is the same as demanding that the set is equal to its closure. It contains all of its limit points. And finally, here's a very important point for our extension theorem. If I have a function defined on a subset of a metric space, one very nice kind of continuity that we'll see will hold in our case is Lipschitz continuity. We say that a real valued function on a subset of a metric space is Lipschitz if there is some positive constant k, so that the distance in the real line between f at x and f at y is no bigger than k times the distance between x and y for any pair x, y in V. That is a K-Lipschitz function. And here is a standard important analysis theorem that we're going to use, which is if f is a Lipschitz function on a non-empty subset of a metric space, then it can be extended uniquely to a Lipschitz function on the closure. Extension, of course, meaning this, that the restriction of that f bar function to the original v is the original function f. And indeed, the extension will have the same Lipschitz constant k. So it would be great if we could turn 2 to the omega into a metric space adapted to the premeasure mu. That's not quite what we're going to be able to do, but it's close. We are going to see that 2 to the omega will be a pseudometric space. Now, what is a pseudometric space? It's almost the same thing, except that we no longer have that implication. So a pseudometric on a set X is a function d on x cross x that is symmetric, satisfies the triangle inequality, and for which d of x equals 0. However, it can be true that there are pairs of distinct points x, y such that the distance between them is 0. That's a pseudometric. And just to give some basic intuition, an example of a pseudometric is in R2, d of the points x1, x2, and y1, y2 could be defined to be the absolute value of x1 minus y1, the distance in the first coordinate. This is a pseudometric. It satisfies all of these conditions. It just doesn't distinguish points because distance 0 simply means that your first coordinates match. It doesn't tell you anything about your second coordinates. So it's kind of like an incomplete metric. Nevertheless, pseudometrics still give us all of the same tools that are written right here. We can still talk about sequences and their limits with exactly the same definition, and nearly everything that you learned in undergraduate analysis still holds. The only issue is that limits are no longer unique. But we don't need unique limits to make any of what we need to work. We still have the closure being the set of all limits of sequences. And we can still talk about Lipschitz functions. Now, notice it is harder for a function to be Lipschitz in the pseudometric case, since the right-hand side can be 0 for lots of pairs of points. So that gives you a constraint on the kinds of functions that can be Lipschitz. They have to take the same value on any 2 points whose distance is 0. But this condition still makes perfect sense, and the same theorem that a Lipschitz function on a subset automatically extends uniquely to a Lipschitz function on the closure works in the pseudometric context. And that is on your homework. We're now going to see how to construct a pseudometric adapted to the premeasure mu. In fact, it will be defined in terms of the outer measure of that premeasure. We start with a finite premeasure, and we define the Cartier-Dore outer measure associated to it, which is a function on all subsets. Its definition, again, is here. Now we're going to define a function on 2 to the omega cross 2 to the omega. It's going to take values in this compact interval of non-negative real numbers, and it's defined like this. The distance between 2 subsets E and F is defined to be the outer measure of the symmetric difference of those 2 subsets. Just to remind you, the symmetric difference is defined to be E minus F union F minus E, indicated here in this picture. This is a pseudometric. Let's see why. First, we need to check that it takes non-negative values. Well, it clearly takes values in 0 up to mu of omega, because it is defined to be mu star of some subset. Now, we need to check that the distance from any set to itself is 0. Well, that's mu star of the symmetric difference of E with itself. But of course, the symmetric difference of a set with itself is the empty set. So that's mu star, the empty set, which by definition of outer measure is 0. We need to see that this function is symmetric, but that follows simply from the fact that symmetric difference is symmetric, also apparent right from the definition. Finally, we are left to check the triangle inequality. And that is on your homework. We have thus constructed a pseudometric which is nicely adapted to the premeasure that we're trying to extend. We will call that pseudometric the outer pseudometric for that premeasure. And in a few minutes, we're going to show that the closure of the field A with respect to that pseudometric is a sigma field. Before we get there, we need a few computational properties of the outer pseudometric. And here they are. We will see that the outer pseudometric respects complementation. The distance between A and B is the same as the distance between A complement and B complement. And we will see that if I have two countable sequences of subsets of omega, then the distance between the union of the first sequence and the union of the second is bounded by the sum of the distances between the terms of the two sequences. Similarly, their intersections are also so bounded. Let's go ahead and check why these are true. For property 1, we simply note that the symmetric difference between A complement and B complement, by definition, is A complement minus B complement, union B complement minus A complement. Now note that set difference is the same as intersection with the complement. So this is A complement intersected with B double complement, union B complement intersected with A double complement. But B double complement is just B, and A double complement is just A. And so this is the same thing as B minus A union A minus B, which is the symmetric difference of B and A, or the symmetric difference of A and B. And therefore, the outer pseudometric of A complement relative to B complement is mu star of A complement symmetric difference B complement is equal to mu star of B symmetric difference A, which is d mu of B comma A, or d mu of A comma B. So that proves part 1. For part 2, A, we're going to use a similar naive set theory fact. If I take an arbitrary union of sets and take the symmetric difference between that and another arbitrary union of sets, I can compare that to the union of the symmetric differences of the terms. These two need not be equal, but we do always have a containment. And that is another elementary fact that you will prove on your homework. Because of that, we can therefore take the distance between those two unions well, that's the outer measure of this symmetric difference. The symmetric difference is contained in the union, and outer measures are monotone. And so we get that this will be less than or equal to the outer measure of this set. But we also know that outer measures are subadditive over countable unions. That's part of the definition. And so that will be less than or equal to the sum of mu star of each of the terms, which is, by definition, the sum of the pseudometric between an and bn, concluding part A. For part B, we could argue very similarly, or we could use part A in conjunction with number 1. Taking complements turns unions into intersections, and if you work that throughout, you'll see that part A turns into part B. Next, we need a lemma, which tells us that convergence in the sense of sets, where a sequence of sets increases to some limit, which is the union of this increasing sequence of pieces, that naive notion of convergence matches up with convergence in the outer pseudo-metric. If we're in a finite premeasure space, and I have a sequence of sets in the field which increase to a set A that may therefore not be in the field, then that set A is in fact in the closure under the pseudo-metric because the distance between an and A tends to 0. And in fact, that distance can be written nicely as the outer measure of A minus the measure of an. Let's prove this. To do so, we convert our increasing sequence into an increasing disjoint union by taking the differences between successive terms. To be precise here, d1 is actually equal to a1, and then for future terms, dn is equal to an minus 1. That means that a, the increasing limit, the union of all the dn's, is of all the an's. That means that a, the increasing limit of the an's, is actually the increasing disjoint union of the dn's. Now, by the definition of mu star, since A is equal to and therefore contained in this union of dn's, which are in the field A, the outer measure, mu star of A, is less than or equal to the sum of the mu of dn's. Let's write out what that countable sum means. It, of course, is a limit, as capital N goes to infinity, of the sum, little n going from 1 up to capital N, of mu of dn. Playing the same game we did in the last lecture, we used the fact that the dn's are disjoint and that mu is a finitely additive measure on the field A. That means we can write that sum instead as mu of the disjoint union of the first capital N d's. But by the telescoping definition of the dn's, that is the same as A capital N. Now, A capital N is a set that is in the field. And therefore, by what we proved in the previous lecture, the premeasure of an is the same as the outer measure of an. Now, an is, of course, contained in A, and therefore, by the monotonicity of the outer measure, this is less than or equal to mu star of A for every n. And since that's true for every n, over here, we get that this limit is less than or equal to mu star of A. And look what happened. mu star of A is less than or equal to each of the terms here is less than or equal to mu star of A. We therefore can conclude that the limit as capital N goes to infinity of the measure of A capital N is mu star of A. Now, that already tells us something really interesting. It says that mu star, which has a fairly complicated definition to start with, can be computed by a limit process. It can be computed by the limit of the measure on an increasing family of subsets filling out A. Great. Now, to conclude the full proof here, we need to repeat what we just said, but subtracting one term in the sequence. So fix a little n. And note that A capital N with A little n removed increases to A with little a n removed. That follows simply from this fact here. And so, repeating the entire argument, or simply applying it to this new increasing family of sets, we get that the outer measure of A minus an is equal to the limit as capital N goes to infinity of mu of A capital N minus A little n. Now, mu is a certainly finitely additive measure on the field A, and both of these sets are in the field A. So, by the finite additivity of the measure, this is the same as the limit, as capital N goes to infinity, of mu of an minus mu of A little n. Now we apply this fact again to this limit to get that this is equal to mu star of A minus mu of A little n. And finally, applying this one more time shows that that limit as little n goes to infinity is 0. And that's just what we wanted to prove. Because you see, since an is contained in A, the difference between A and an is the same as the symmetric difference, since an minus A is the empty set. And so this is equal to mu star of the symmetric difference, which is nothing other than the pseudometric distance between A and an. And that concludes the proof. Now, an immediate corollary, as we stated at the beginning, is that if I have any such sequence, an, in the field that increases to its union A, then that increasing limit is actually in the pseudometric closure, because the distance between an and A is tending to 0. This puts us in a position to prove the first half of the extension theorem. Namely, in a finite premeasure space, the pseudometric closure of the field A is a sigma field. We just need to verify the 3 definitional properties of sigma fields. 1, we need to check that the empty set is in a closure. Well, the empty set is by definition in the field A, and the field A is contained in its closure in the pseudometric space, and therefore the empty set is in the closure. 2, we need to check that A bar is closed under complements. So, fix some set in the closure. We need to show that its complement is back in the closure. What does it mean that B is in the closure? It means that there exists some sequence, an, in the field A that converges to B in the pseudometric. Well, if I take the metric distance between an complement and B complement, by the first property we proved for the pseudometric, that's the same as the distance between AN and B, which goes to 0. And that means that AN complement goes to B complement. Now, AN complement is back in the field because the field is closed under complements, and therefore B complement is a limit of a sequence in A. It is therefore in the closure, which is what we wanted to show. And finally, 3. We need to show that A bar is closed under countable unions. So, let's suppose that we have a countable sequence of sets, Bn, in the closure. So for each one of those, I can find a sequence that converges to it. And we're going to perform a diagonal sequence type construction, but we'll do it using the same epsilon over 2 to the n trick that we've used a couple of times now. Fix some tolerance epsilon, and for each n, we can find some an in the field whose distance from Bn is as small as we like, because Bn is in the closure, so we can make it less than epsilon over 2 to the n. Well, that means that the distance between the union of the ANs and the union of the BNs, by the second property of the pseudometric that we proved, is less than or equal to the sum of the distance between AN and BN, which we've constructed to be less than or equal to the sum of epsilon over 2 to the n, which is epsilon. So that means that we can find a set here, a union of the ANs, which is within any small distance that we want of the BNs. Now, that doesn't quite finish the proof, because this union of the ANs is a countable union of sets in A. It is not necessarily in A. But on the previous slide, we showed that if I have an increasing countable sequence of sets in A, then their union is in the closure. And so these guys are in the closure. And so what we've shown is that the union of the BNs can be approximated by things in the closure. And the proof will be finished by noting that the closure is closed. So if we want to be more pedantic and precise, we can say for each m, where m here is 1 over epsilon, what we've done is to find a set AM closure. That's going to be this one here. This is A 1 over epsilon closure, which is, by the previous slide, in a closure such that the distance from AM bar to the union of the BNs is less than or equal to 1 over m. Well, it follows from there that this sequence AM bar converges in the pseudometric to the union of the BNs. The AM bars are all in a closure, and therefore this union is in the closure of the closure, which is the closure. And that's what we wanted to show, that the union is back in the closure. That demonstrates finally that this closure is a sigma field. Next time, we will use similar tools to show that the premeasure mu has an extension to this closure, and that that extension is a countably additive measure, proving the extension theorem.